Next up, let's consider the following example. We are going to convert the following double integral into polar coordinates and then evaluate the given integral. We have the integral from 0 to 1 and the integral from x to the square root of 2 minus x squared of x plus y dy dx. Now, first thing that I want to point out here is that the first integral that we're supposed to do is with respect to y, and the second one is with respect to x. That means that we can interpret this as being a type 1 region. So being a type 1 region, this tells me that y is in between x and the square root of 2 minus x squared, while x varies from 0 to 1. So what I'm going to do is try to interpret all of these as boundaries of our region and see if we can actually sketch the region in question. So first off, if we have, let's do boundaries. It's important to respect your boundaries. We have y is equal to the square root of 2 minus x squared, and a little bit of algebraic manipulation lets us know that that is equivalent to x squared plus y squared is equal to 2. That would be a circle centered at the origin with a radius of the square root of 2. So we'll draw it in the other regions, even though we're definitely not going to need those regions. So square root of 2 here, square root of 2 here. We're also told that we have a boundary that is y equals x. That'll be simply a straight line passing through the origin, slope 1. Now, if y is equal to x and we plug in x equals y to this equation right here, we'll get that x and y are both equal to 1, solving using a little bit of algebra. Now, we also want the circle to be the upper boundary and the line to be the lower boundary, while x goes in between 0 and 1. That means that the region in question, circle is the top boundary, line is the bottom boundary, in between x equals 0 and x equals 1. This would be the little slice of the pie that we're talking about here. I would like to convert this from rectangular coordinates or Cartesian coordinates into polar coordinates. I think we already made a pretty solid argument for r. R is going to start at 0 and go directly out to the edge of this little circular region. That'll be from 0 to the square root of 2. Now, as far as theta is concerned, we've established pretty well in our trigonometry courses that the angle that goes straight up is going to be pi over 2. The other angle is defined by the line y is equal to x. Now, if I take y is equal to x and I convert both of these into polar coordinates, I would have that r cosine theta is equal to r sine theta. Taking r out of the picture, that means that the sine of theta would be equal to the cosine of theta. And there's only one point at which this occurs in quadrant 1. The angle at which this occurs in quadrant 1 is theta is equal to pi over 4. That'll be the lower bound for our region. That way we can start at pi over 4 and then rotate on over to pi over 2. So, 3 things that we need to change for our double integral. Let's recopy what the double integral was. That's 0 to 1, x to the square root of 2 minus x squared, x plus y, dy dx. So, things that need to change. First off, we'll start with theta. That'll be pi over 4 to pi over 2. And then r will go from 0 to the square root of 2. Changing our integrand, x is r cosine theta, plus y is r sine theta. Dy dx is equivalent to dA, and dA in polar coordinates is equivalent to r times dr times d theta. Once in this form, it is possible to factor our integrand into a function of x times a function of theta. A function of r times a function of theta. I don't know where that came from. So if we were to distribute the r through, we would have an r squared on both of these terms. Factoring that out would leave us with r squared. We would also have cosine of theta plus sine of theta, dr d theta. Applying Fubini's shortcut, and we'll move this over to the far left side of the page to give us a little extra space. This will be the integral from pi over 4 to pi over 2 of the cosine of theta plus the sine of theta d theta times. The function of r is simply going to be r squared. And bounds on that will be from 0 to the square root of 2. Performing these integrals, cosine of theta will become sine of theta, plus sine of theta will become minus cosine of theta. That's going to go from lower bound pi over 4 to upper bound pi over 2, times 1/3 r cubed, going from 0 to the square root of 2. Simplifying each of these, we'll start with the theta functions. The sine of pi over 2 minus the cosine of pi over 2. Sine of pi over 2 minus the cosine of pi over 2. Minus, and then plugging in the lower bound, sine of pi over 4 minus cosine of pi over 4. Then for r, we will have 1/3 of the square root of 2 cubed minus 1/3 of 0 cubed. This is going to simplify so much. Sine of pi over 2 is 1, cosine of pi over 2 is 0, sine of pi over 4 and cosine of pi over 4 are equal to each other, so their difference will wind up being equal to 0. This entire set of brackets becomes 1. When I cube the square root of 2, I'm going to get 2 square roots of 2, and that'll still be over 3. So final answer for this one is going to be 2 square roots of 2 all over 3. Just less than 1.